Okay. All right. Thanks, everyone. Good morning. Yeah, so my name's Jason Zhang, and today I'll be presenting my final project, which is a topic on de-randomized algorithms and de-randomization. So, yeah, so for this topic, I've chosen, I believe the third option for the final project, which is the textbook exposition. So I'm going to be expositing, or I'm going to be presenting the section of the topic, the section of the textbook, which roughly corresponds to section 5.6, I believe. Um, which is the section on de-randomization, but also in reality, so I'll be presenting material from a couple other sections as well, I believe like 5.4 or 5.5, because I'm going to be examining a couple different problems in this lecture, and one of these problems is declustering, which is a problem that we have not discussed in lecture, but I'll be presenting the problem, and I'll give like a first a randomized algorithm to solve it, and then I'll give a de-randomized algorithm. Um, which can solve the problem deterministically. So actually, I'm going to draw from like a couple different sections of the textbook here. Okay. Um, yeah, so also for this final project, in addition to this video lecture, I'll also be um, producing a set of scribe notes for a couple different lectures throughout this course. So it'll be the topics on de-randomized lecture on randomized algorithms. So if you remember, like way back, like near the beginning of the course, we had a couple lectures on randomized algorithms, reviewing like the longest path problem and things like that. And so yeah, if anyone wants like a quick refresher um, on like the methods and the constructions that we used in those lectures, like to in order to tackle randomized problems, you can read like a quick like review of that. Um, and also, yeah, okay, all right, so let's get started. Okay, yeah. So first, let's motivate de-randomized algorithms. So in this course so far, we've seen several examples of randomized algorithms that can succeed with high probability. So if you remember, like way back in the day, like in the first like one third of the course or something, we investigated a couple problems which were like feedback vertex set and longest path and subgraph isomorphism. And in each of these problems, we used some like randomized techniques. Um, Specifically, we use like techniques such as like color coding and things like that in order to solve these problems with high probability. And oftentimes we can repeat some sub procedure like a given number of times in order to achieve like arbitrarily high probability. So like for any epsilon, we can produce an algorithm that like succeeds with probability greater than 1 minus epsilon. However, these randomized algorithms have the very important caveat, which is that they don't actually succeed with probability 1, which is that even though we're able to produce arbitrarily high probability approaching 1, we can't actually guarantee success in any of these. And so sometimes we would like to guarantee success and succeed with probability 1 with still a reasonable runtime. And so, yeah, today we're going to achieve this. Yeah, so today we're going to be studying two different problems. We're going to show how to solve the longest path problem deterministically with good runtime. And we're also going to study declustering, which is a new problem. So I'll define the declustering problem, and then as I said before, I'll present like a randomized algorithm for solving declustering with good probability, and then we'll show how to de-randomize it and how to make it deterministic. So roughly speaking, both of these problems follow like a similar rough framework, which is that they both use like color coding, and as well as like a pseudo-random construction, which I will define and explain. Okay, so these are the contents of this presentation. So it's as follows. So first, I'm going to define some basic pseudo-random objects as an introduction. Um, yeah, and unfortunately, this section has a bit of a caveat, which is that so the textbook doesn't cover actually how to const so we're going to define some pseudo-random objects, and then unfortunately, we can't actually show an algorithm on how to construct these because it's not covered in the textbook, and unfortunately, it's like beyond the scope of this course, basically. Um, And so we're just going to like define these objects and just state as a black box that we're able to construct these with some reasonable size and some reasonable runtime, and then we're just not going to prove, unfortunately. So during the randomized algorithm lectures, we saw some examples of these. For example, using error correcting codes, we produced like some construction. And then yeah, I guess if you're interested, you maybe just like maybe you can like look this up to see how these are actually done. I don't actually know how these are constructed. Okay, after that, we're going to study longest path. And so before we study longest path, I'll give like a brief recap of how we did it in lecture and like some of the basic constructions and stuff that we did. And then we'll de-randomize that algorithm, and then we'll study the declustering problem. So again, I'll give like an exposition of the problem, an algorithm to solve it with high probability, and then an algorithm to solve it with probability one. And then as a bit of a bonus at the end, this was not actually in the textbook section for this project, but as it turns out, so this semester, in addition to this parameterized algorithms course, I'm also taking the graph algorithms course with Tatopong Saranarak. And just as a coincidence, in that course, in our final project, we're also investigating an algorithm which can be de-randomized. And so we're actually seeing like I'm actually seeing de-randomization in several different contexts right now, in these different projects. And so I'm just going to like give like a very, very brief, like high level exposition of like what's going on in that other project. And I'll maybe like define the problem and just give like a like just say a few words about it, just because I think it's relevant to this topic and just because I think it's interesting. So I'll talk about de-randomization in other contexts. Okay, so let's start. So our basic pseudo-random object in this context is a splitter. And so this is the definition of a splitter. So an NKL splitter F is a family of functions that goes from the integers of n to the integers of L, such that for every subset of size k, there exists a function that splits S evenly. And basically what that means intuitively is that you can see that for any, roughly speaking, splitting something evenly means that for any element in the codomain, its pullback is basically like of the same size. Just like every element has the same size pullback. And then we allow this like differing by at most one, which basically just means like just because like we're like rounding to the nearest integer or something. So yeah, I'm just like it just allows you to like round in the nearest integer. But basically, intuitively speaking, like the pullback has to be the same size. And then we can observe that the intuition of a splitter is that basically if we think about color coding the domain of the function, we can think of splitting as basically like each color should be used roughly like the same amount of times if the color represents like the element that this is mapped to, basically. So if the codomain, like these integers of L's, is going to be like a set of colors, which in practice that's actually what it's going to be, then we have this intuition. Also, we can observe that if L is at least K, this definition of splitting evenly basically exactly means that F must be injective on S. Okay, and so now here's our first black box for the day, which is that for some reasonable size, we can construct a splitter of a desired size with a desired runtime. And so this is like k to the O of 1 log n, and in time k to the O of 1 n log n. So I should just remark here, I should just point out that this construction runs in like relatively good runtime. We can see here that the runtime is only linear in the size of the construction. And so this is significantly faster than some of the constructions that we've seen in this course, which often run with like very high runtime and stuff. So this is like, yeah, this is like a pretty efficient black box in some sense. Okay. And a special case of a splitter is called a perfect hash family. So this is an NKK splitter. We just call it an NK perfect hash family. And this is, yeah, this is our second black box, which is that we can construct a perfect hash family with also some desired runtime. And I should draw attention to this definition, that this definition is especially important to us because if we think about what is actually going on in the longest path function, if we recall, um, we were trying to color code the vertices of some ambient graph G, which has n vertices, and we're trying to color code it um, with exactly k colors. And then we were trying to achieve some like combinatorial color coding property. And so we can kind of notice here roughly, like one can kind of feel that an NK perfect hash family like roughly corresponds to this definition. And indeed, like later on, we're going to use a perfect hash family in order to actually tackle the longest path problem. So this is a nice construction. Yeah, so now also we have to talk about k-wise independence. So basically a k-wise independent sample space is just a function space such that if you have any k tuples, basically you achieve like probabilistic independence across like these tuples. So definitions like this. So maybe you've seen this in like an analysis course or something. And then another black box is that we can construct one of these quickly. And in reality, so this is the definition of k-wise independence, but in reality, we're actually only going to use two-wise independence or pairwise independence. And so this is the same exact definition, um, but I replaced k with two, so this is a special case. And then I'll draw like particular attention to this construction, which is that a pairwise independent space has size O of n squared, which is important. And as with all the other black boxes that I've presented so far, all of these constructions can be constructed efficiently in time that is linear in the output size. So that's very important because at the end of the day, we're going to try to achieve some algorithm that has like relatively fast runtime and relatively small like increase of runtime with respect to the randomized algorithm. Okay, so let's talk about the longest path problem. Yeah, so as a review, if we recall the longest path problem from previously in this course, the problem is that we have an ambient graph G and some integer K, and we want to just see whether there exists a simple path in G of length K. So it's a relatively simple statement. And um, yeah, so recall a simple path in G is a path of vertices where every vertex in the path has to be unique. So we can't have any like repeating vertices. And this is important because um, for example, if we were to just allow any path, this problem would be kind of trivial because we could just take like some edge A and B, and then you could just have a path which just goes like in between A and B and just keeps going back and forth. And then so that's not very interesting. And if we recall, the way we tackled this problem was, oh, actually, interestingly enough, we actually solved this problem in multiple ways in this course. So if we recall, like we first did like a randomized algorithm for this, and then like later on, we also gave like a polynomial, like an algebraic method for solving this problem too, where we use like a field of characteristic two, like a finite field, and then we use the construction that like if we set up some polynomials corresponding to like um each like attempt at a simple path, we can basically get some polynomials that like cancel out modulo two. And we used the fact that like the factorial of any integer greater than one is necessarily even. And so then everything like cancels out like in characteristic two, and then we get like some really nice, like some really like beautiful algebraic fact or something. Yeah, but in this case, we're like focusing on the randomized algorithm. And in this algorithm, our technique was roughly that we randomly color the vertices of G with K colors, and we just hope for two things. So the first thing is we hope that we get like a good color configuration. Um, and then the second thing is that we hope that a good color configuration can actually happen with high probability. And that allows us to like iterate and repeat this algorithm many, many times. Yeah, so rigorously, this is what's going on. So let's say we have a coloring chi of the vertices of G, and then we define VI, and then basically we have this like dynamic programming type like statement, which is that we can consider like um, yeah, so we can consider this path function, this statement of path of S and U, which we define to be true if there's a path that starts at some vertex and then ends exactly at U, and that it basically like touches every single vertex in this set S. And the reason this is like very amenable to dynamic programming is because we can we can consider like if we have a partial path of length, let's say like k prime for some k prime less than k, we can consider the last vertex in this path, and then we can consider like the one before that, so like the second to last vertex. And then we can just sort of do like DP on like the all of the set of possibilities of what the second to last vertex is. And so exactly this is what this is. So the path of S and U with respect to this coloring chi is basically like the logical or basically like it's all the possibilities of all of the possible second to last vertices. So those are all the vertices that are the neighbors of U, but not like this like bad coloring property basically. So we always have to maintain this invariant, which is that every color is used exactly once. And then of course at the end there's like this trivial fact, which is that if two vertices have different colors, then they must be different vertices, which is how we solve this problem. So we have this longest path helper, this algorithm, which we have our longest path helper is basically that we can choose some coloring chi, which is a uniform random coloring. And then we let V1 be the start of the path, which we can compute in time like O of n. And then using dynamic programming, we can compute like the path of K and U. And the reason this runtime is good is because um, this runs in roughly time 2 to the K, or it runs in time FBT and K. And then um, we have this analysis at the end, which is that if there actually is some K length path in G, each vertex is assigned a unique color with good probability. And so we have this probability like K factorial over K to the K, which we said is some function of E. And then yeah, and so we succeed with high probability, and then we can repeat this algorithm with this many times basically independently to succeed with high probability. And so this is just like a basic like probabilistic analysis at the end, which I'm gonna omit the details because it's not that relevant. Okay, so now let's de-randomize the longest path. So I just want to like recall this definition from a previous slide, which is the definition of a perfect hash family and the construction of a perfect hash family. All right, so now our algorithm is that um, yeah, so our de-randomization is that we can construct this perfect hash family, which we'll call F, like this fancy F. And then for each function in the hash family, we can just set a coloring to that function, and then we can just iterate through this perfect hash family and just compute the exact same dynamic programming statement as before. But now instead of like randomizing each time, we're just using like the next one in this perfect hash family. And the reason this works is because of the property of the perfect hash family. So if we recall, like we maintain a splitter. We maintain like the hash family, and then yeah, like necessarily some function in this hash family will be injective on its vertex set. And what that corresponds to is that it means that if there exists some path in G, every vertex of this path will necessarily receive a different color. And so that way we'll be able to detect it using this de-randomized algorithm. And the runtime is depends mostly on the runtime of the construction of the hash family, which we said was good. So we run it with this runtime, and then we run it with a store of like 2e to the k times like some small like perturbation of k. So if we compare this to the randomized runtime, it's worse, but not that much worse. And so actually like yeah, this is like a good improvement because we make it deterministic, but then we actually don't lose that much in runtime. So it's very good. Yeah, so now I'll just like very briefly state something about the longest path problem, is just that like in the textbook, um, there are other ways of randomizing the longest path algorithm using divide and conquer. So there's this other algorithm where we can basically divide up, like we can recurse on a path of length k and divide it into like two paths of length like k over 2. And then we can kind of like recurse and do some really fancy construction. But unfortunately, like the analysis of this construction is quite tedious and it's quite long basically. And also the while the randomized algorithm I think is interesting, the de-randomization of it is not that interesting. And it roughly follows like the same structure as the structure that we just presented. So I think we're just going to omit this. And I think like, yeah, it's better to just present like the declustering problem because I think the de-randomization of that algorithm is more interesting. Okay, so let's talk about declustering, which is like the main meat of this lecture. Okay, so first we define a cluster graph. Is a graph which is just like a bunch of disjoint clicks. So every connected component of H must be a click, which is a complete graph. And we also define an adjacency set, which is like just a set of pairs of vertices, and not necessarily edges, but just pairs of vertices. And then we also define this like direct sum of like G. I'll just pronounce it as like G sum A. And G sum A is the graph that has the vertices, the same vertex set of G, but it has the edge set, which is the symmetric difference of the edges of G and A. So basically, what that means is that like we take the edges that are uh, in G but not in A, and then union that with the edges that are in A but not in G. And so intuitively, what that means is that if we're allowed to choose what we want for the set A, basically what it means is we can both like add edges to G and we can also delete edges from G, based on like what we choose to be in A. And the problem of declustering is that given a graph and an integer K, we want to see if we can change. Oh. Yeah, we want to see if we can change G into a cluster graph by using like relatively few, like at most K, um, like changes to the adjacency set, such that G sum A will be a cluster graph with D components. Yeah, so this problem is like an edge modification problem, which is a little bit different from um, like the longest path problem, because in the longest path problem, we're not actually changing the graph G. We just have to like detect some stuff. But in this problem, we actually get to change the graph G. Yeah, so as I said, the intuition of this problem is that we can try to like uh, modify some edges to G. We can both add and delete to try to make it into a cluster graph. And we want to do this with few modifications. So we're going to use like a similar like color coding technique to do this. Okay, so let's give a high level overview of how to attack this problem. So roughly what we're going to do is this is similar to the longest path problem, which is that we're going to take the vertex set of this ambient graph G, and we're just going to like randomly like scatter it with Q colors, which we'll define Q later. And then we're going to follow like the similar structure, which is that like if there actually is a solution A and G, we hope that A will be like properly colored. So we hope that A will receive some good coloring configuration. Um, oh, and by the way, yeah, properly colored here. Oh, did I define it? Okay. I think, yeah. So properly coloring of an adjacency set just means that for every pair in the set, like B, like A and B have to receive different colors. So it's like basically the same definition as a proper coloring of a graph. Yeah, maybe I should have written it. Okay, yeah. Um, so basically we hope that A will be properly colored in G. Um, and then so now we need to justify like two different things, like two different pieces of intuition. So the first one is that like if A is actually properly colored, that this is the best case scenario. And then in this case, like I hope that I can solve the problem in good runtime. And the second thing is that I need to justify that a proper coloring of A actually happens with high probability. So far, this is like still pretty analogous to the longest path problem. Oh, okay, yeah. So here's the definition of proper coloring. So it's just, yeah, it's like the same as proper coloring for a graph. And so first we're going to use this lemma, which is the high probability of a proper coloring. So let's first justify that if we have a graph G with K edges, um, that we actually get like with high probability, um, we get that like this graph is actually properly colored. So we're going to set Q as the square root of 8K, like rounded up to an integer. And also I'm going to ignore like the rounding of integers here. So yeah, we can just assume that like either assume that like K is a perfect square or just assume that all these numbers are like big enough that it like doesn't matter. Yeah, so if we're going to set if we color G independently with this many colors, then we receive high probability that the edge set is properly colored. Okay, so let's prove this. So we're going to construct a sequence of graphs starting from G, where basically at each iteration we're going to remove the lowest degree vertex um, from GI. And so we'll start with G0, which is G. We'll remove a bunch of lowest degree vertices so that when we get to Gn, that will be the empty graph, so it'll have no vertices. And then let di be like the degree at each iteration. Okay, so let's study like the degrees of each of these things. So trivially, like di is it has to be less than the number of vertices. And then also, since this uh since this vertex is of minimal degree in graph GI, we can have this inequality. So like the di times like the number of vertices is less than two times the number of edges, which is like the total degree in a graph, which is also 2k because k is the number of edges in G. We have these two inequalities, and then when we combine them, we get that like di squared is less than 2k, which means that di is less than the square root of 2k. Yeah. Now let's consider what happens if we just like randomly color these vertices in backwards order. So we start from V1, Vn, and then we go to Vn minus 1, and then we go all the way backwards to 1. Um, and let's say we color these with Q colors. So what happens in this iteration? So let's say like let's try to bound like intuitively just try to bound the probability that a good coloring appears. Uh, And so let's say we start with Vn and we try to color Vn using some like proper coloring. So in this case, it's trivial because it's the first vertex. And so Vn is going to be properly colored with probability 1. Then when we try to color Vn minus 1, we can color Vn minus 1 with any color except for the color that we already used for Vn. And so intuitively, this should be high probability. And then when we go to Vn minus 2, we can use any color except for like the two colors that we have already used. Um, And so intuitively, at each iteration I, there's going to be at most like the square root of 2k, like bad coloring decisions, like coloring decisions that don't work, that would cause an incorrect coloring at each iteration. And this is because of like the property that we established on the last slide. So if we remember, like di is less than 2k, and so the only way you can like mess this up is if you give like one of these like at most root 2k bad colorings. And so what we obtain from this is that the conditional probability at each iteration, like the probability of pi minus 1 being correctly colored, given that pi is correctly colored, is at most this expression. So we have like the total number of like the number of good colorings is at least the total number of colorings minus the number of bad colorings, which is at least q minus di, and then in total there's q possible choices. So this is at least 1 minus di over q. And where, yeah, so here we define PI to be the event that the edges of the graph GI are properly colored. And then at the end of like at the end of the day, for like in order to prove this lemma, we want to bound the probability of P0 happening. So here we use this analytic lemma, which we're not going to prove, like 1 minus x is greater than 2 to the 2x for this bound, for this domain. And then, yeah, and so at each iteration, the conditional probability, the probability of pi minus 1 given pi, is less than this probability. Okay, so now we can iterate through this conditional probability. Like the probability that the edges of G are properly colored is we want to bound the probability of P0, um, which is basically the sequence of conditional probabilities. So we can break this down, and so we get like this is the probability of Pn times the product of all of the conditional probabilities at each iteration. And remember, we said that the probability of Pn is 1. And so we get like 1 times this probability, 2 to the negative 2 of di over q. Um, which is, yeah, and then after simplifying some terms, after moving some terms around, we get that this is like 2 to the negative 2 over like the square root of 8k. And then we just use that like the square root of 8k is 2 times the square root of 2k. Um, and so then yeah, then we get this probability. And so this um yeah, this completes the proof of the lemma. Okay. So now we've shown that like this proper coloring happens with some good probability. And so now we then it remains to basically justify why like we actually want this to be desirable. Like why do I actually want a perfect coloring of the set A? And so let's study what happens here. So we claim that if G is a graph and we have like a coloring chi of the vertices of G such that um, if there exists a declustering solution A which is properly colored by chi, then we claim that each like the induced graph on each coloring set VI is necessarily a cluster graph with at most D components. Um, yeah, and so what this means is that like basically we're going to use this lemma to study that each cluster graph has at most D components, and then we're going to try to combine them in some creative way in order to obtain a declustering solution. So this lemma is relatively straightforward. So all we need to do to intuit this is observe that like um, if we assume that all of the adjacencies in A are all properly colored, so that they're all not in any G-induced VI, then each of these graphs must be an induced subgraph of G sum A. And this one has D clusters. So the reason it must be an induced subgraph is because like if every adjacency in A is properly colored, then basically no adjacency in A can have like the same color, which means that they cannot be like excluded in any like G induced by VI. So basically we know that like all the edges are necessarily there in this induced subgraph. Okay. Okay, so um now that we're given that each induced graph of G on VI um, must be a cluster graph, we can observe that every click, like every component of this graph, must be contained in some component of G sum A. And so when we like go back to the actual ambient graph, basically, like that ambient graph is also going to have like some cluster components. And so this like basically each of these small components must be inside one of the big components. And we know that there are at most D components. And so what that means is we can obtain this bound for like what happens if we just like guess the configuration. Like the configuration meaning like the assignment of each of these clusters to each of the like the big clusters of G sum A. So formally, if we analyze this, G sum A has, let's assume it has D components. And each induced subgraph of G on VI has at most D components. And what that means is that in total across all of them, there's at most DQ components. So if we try to guess this configuration, if we just iterate through every single possible configuration, well, then there's at most like D to the power of DQ components. Um, just by this like simple like counting argument. And then which is like D to the DQ, which is like D times like the square root of 8k. And then yeah, and this is numerically equivalent to like 2 to the O of D log of D times the square root of k guesses. And so intuitively, what's going on here is that um, we can sort of guess the rough configuration of each induced subgraph based on just like a sort of like brute force argument. Yeah, and then once we have the correct configuration, it's very easy to construct the adjacency set A. So for each iteration, we can conclude that we can just construct A by just like trivia. It's very obvious what we need to do. Like we just need to like add in the necessary edges into A and also just like remove the necessary edges from G in order to make this a cluster graph. And so in each iteration, we can just construct A and then we can just like see whether A has size like less than or equal to K. And okay, and so this basically concludes the intuition of this lemma. Yeah, and so this is the lemma that we have just proved. This lemma up here. So the sub procedure given a coloring. So given an instance of a clock. of declustering with a coloring chi, we can basically test whether chi is like a good solution in this time. So in O star of this runtime, which we just established from the previous analysis. And then we're going to set a small black box because it's not like really the main topic of this lecture, which is that like given this testing of each coloring, we can basically test um, the properly colored solution of all colorings in this rough in this rough runtime. And this basically reduces to like a bit of a dynamic programming exercise about different colorings. And we're just going to omit the proof of this because it's not that enlightening. So we're just going to cite this in the textbook. Okay. And so in conclusion, what we've shown throughout all of this analysis is that we can produce like a randomized algorithm for declustering running in this runtime in 2 to the O of D root K, succeeding with high probability. And then we repeat like the same analysis as in the longest path case, which is that we can repeat this algorithm many times and then we can succeed with arbitrarily high probability. So this basically concludes the randomized algorithm for declustering. And now, as promised, we're going to de-randomize it and we're going to show how to make this deterministic. Okay, so we're now going to use the previous constructions and we claim that declustering can be solved deterministically um, in this runtime. And I also just reproduced the statement of the problem here just in case we want like a refresher. Okay, so the intuition is we're going to roughly reproduce the same structure as in the longest path problem. So we want to like produce some pseudo-random object, which is sort of like exhaustive in some sense. And then we want to just like iterate over this object, and then just use some like exhaustive guarantee property in order to like guarantee that some function in this pseudo-random object is actually going to have like the desired property that we want. In order to do that, we're going to define this new definition, which is a coloring family. So an NKQ coloring family is a family of functions that goes from the integers of n to the integers of q with the following property, which is that like um, so for a graph with n vertices with at most k edges, there exactly exists a function in this family that properly colors the edge set. And so intuitively, one can kind of see how this would be like very relevant. This is basically like the exact object that we want in order to solve this declustering problem. Also, this Q here in this definition, I used the same letter because this is actually going to be like the same Q that we defined on the previous slide. Yeah, so we have to omit a bit of details here, which is that like in order to solve this problem in the general case where a graph can have n vertices, it suffices to basically solve the case where we have k squared vertices. And so we can reduce this case, and then in order to actually reduce, like in order to actually solve the general case here, we can just compose this with like an nk k squared splitter. And just you can just do some like trivial function composition and everything just kind of works out. Like, um, yeah, there's like a brief explanation in the textbook for this. But our crucial lemma here is that we can basically construct this k squared k 2 root k coloring family of the desired size, and it can be constructed efficiently. So again, this is in a runtime that is linear in its size. So in order to solve this, let's go all the way back to the beginning of the lecture where we define a pairwise independent sample space. And let's let this fancy G be a pairwise independent sample space. Yeah, so let's recall that every function inside G goes from the integers of k squared to the integers of q. And also recall like the bound on the size of G from like way back when, which is that the size of G is at most on the order of k to the fourth. Okay. Now let's construct F. So basically for every function inside this pairwise sample space, this pairwise independent sample space, and every subset of the vertex set with size Q, um, we're going to define like this little function, like this subfunction F of G and T, which is um, intuitively speaking, like what happens is that this function is going to be the same as G on the vast majority of all of the elements of the domain, except for on this set H, where it's going to give like it's going to be like Q, so like the max allowed size plus this J coloring. And the reason, like the intuition for what this does is like there's like these two very crucial observations here, which is first of all that like yeah, so F from G to T assigns it in a color not in the integers of Q, but in the integers of 2Q. And the reason this is important is because every element in the set H is going to get its own unique color. And so, yeah, then every element having its own unique color is going to be very useful when we try to justify that these functions give like a proper coloring of some edge set. And so intuitively, if you can think of the vertices of H as being roughly like um, if you can roughly think about H being the set of vertices of the edge set, if each of these vertices are going to each have a unique color, it's going to be very easy for us to justify like why there's a proper coloring overall. And then in order to define F, we're just going to put like F, the fancy family F is just going to be all these subfunctions. So every function of G and T for every like G inside the pairwise independent sample space and every T, which is a subset of the desired size. Okay, and then yeah, the runtime all checks out based on these previous constructions, and then now it remains to just justify why this fancy F is indeed the coloring family that we claim. Okay, so what we need to show is um, for any graph on k-squared vertices with at most k edges, we need to show that there exists some function in this family that properly colors the edge set. So let's fix such a G, and then we'll rigorously construct um, an element of this family which properly colors it. So intuitively, you might think that like, yeah, one strategy that we might try to do is like we know that G has like a bounded number of edges, we can just take like one endpoint from each of the edge set, right? And then like just scatter all of them and just hope that they all get a different color. But then there's actually too many. So we bounded T, which has size Q, which is the square root of K. So we need to do like something else here, not like something non-trivial here. And that's where we're going to use the fact that G is a pairwise independent family. So given this probabilistic bound, we can use the pairwise independence to basically show that the expected number of monochromatic edges with respect to this coloring is at most the square root of k. And what that means is that essentially it means that like if we recall, like monochromatic edges are the only edges that are relevant when you're trying to like produce a proper coloring. Like the edges that are like properly colored anyways, like you sort of don't have to worry about them, and then you only have to deal with like this very small edge set. So the proof here is relatively straightforward. If we consider just some fixed edge, by the pairwise independence property, the probability that this edge is monochromatically colored with the color Q is with the yeah with some fixed color J is exactly 1 over Q squared, and then there's Q colors, and so the probability that it's monochromatic is 1 over Q. Then we just do this like sum of expectation, and we get that the expectation of the number of monochromatic edges is the square root of K. So, by the expectation property, necessarily there exists some function g inside this pairwise independent family that admits at most q monochromatic edges. And then it's very easy to just let t be a set because t also has the bound that it can have size q. And so t can just be a set containing one endpoint of each of these edges. And then if you recall that the property of T is that like basically all the elements in T are like very like scattered very well in the set of colors. And so therefore like the function of G and T necessarily properly colors the edge set. And so this is like a very nice, like in my opinion, a very elegant construction. And this completes the construction of the pairwise family. So this completes the proof of the crucial lemma. And so now our final algorithm is that using these previous lemmas, um, we can construct this family as follows. So basically we can solve the declustering problem as follows. So we basically run the same algorithm as in the randomized construction, except instead of doing the randomized component, we just replace it with iteration over this very well constructed family. And intuitively, this is similar to the construction that we did for the longest path problem, where we also iterated over like a perfect hash family. So this time we iterate over like a coloring family. And finally, the final theorem that we proved is that the declustering problem can be solved deterministically in this time, which is like 2 to the O of root k and d plus log k. Okay. Okay, nice. So now I want to give a slight bonus topic, which is de-randomization in other contexts. So as I mentioned previously, I was actually investigating de-randomization this semester in another course too, and I only want to mention this in this project because it's so relevant. And also because we were using it to solve like a min-cut problem, which is also relevant to this course, because when we were studying like shadow removals and advanced cuts and things like that. And so in this lecture, we only investigate de-randomization schemes that use like iteration over a pseudo-random object. So that's why we constructed these things such as like splitters and perfect hash families and coloring families and these pairwise families and things like that. We construct all these families such that they all contain like some exhaustive combinatorial property. But in reality, there's also other ways to de-randomize to de-randomize an algorithm. And one such example is a thing called a pessimistic estimator, which is kind of different. So in this case, we use conditional probability. For example, let's say we have like a sequence of events that we have to do, like a sequence of choices that we have to make. And then we have to make these choices in a way such that, um, like globally, we satisfy some like constraint. Let's say we have to choose like the edges of a graph, and our global constraint is that we can only choose like a small proportion of the total edges of the graph or something like that. Um, in this case, we can kind of bound the expected number of like bad events. So in our example, it would be like the like choosing an edge of a graph is a bad event because it if you choose too many, you can like violate the constraint. And then we can use this method of conditional expectations, which is that we can fix the random choices one at a time such that we have this like bound of intuitively like the badness of like the global badness of the algorithm. And then we want this like expected badness to never go up. And this is what we use with conditional expectations. And a pessimistic estimator is basically like an analytic approximation of this bound, such that it will never go up. Um, in our example, when we're picking the edges of a graph, we can always just when we're iterating on some graph E, we can always just choose whether to like include E or not include E. And we can always, by linearity, we can always pick the option out of these two, which keeps the pessimistic estimator score as low as possible. And then once we finish the algorithm, the pessimistic estimator is basically like a real number, which will start strictly less than one, and it will only decrease from there. And it represents an upper bound on the probability of failure of the algorithm. So if at the end of the algorithm, this number is still strictly less than one, then we necessarily succeed. Okay. And so this is actually the problem that we were trying to solve in this other research problem, which I'll pull up here. Yeah, so we were trying to de-randomize this paper. Hopefully you guys can see this in the recording, which is we were trying to solve like we were studying this paper which de-randomizes an algorithm to solve like a min cut in almost linear time. And the way they do this algorithm is very cool. Like um they have like um a random construction of a graph, and they use this pessimistic estimator as the exact algorithm that I described, which iteratively chooses an edge, or chooses to include or not include an edge in the graph, um, based on like the method of conditional probability in order to satisfy some bound at the end. which is that like a skeleton graph like basically approximates intuitively it approximates min cuts in an ambient graph with very good runtime. And so this is exactly like the kind of de-randomization thing which I'm learning more and more is like very common in other fields of algorithms. And so I think this is pretty interesting. Okay. So yeah, thanks for watching. I hope you learned something, and I hope that de-randomization is an interesting topic to you as well. It was definitely very interesting for me, and I think I enjoyed reading this section of the textbook and learning about these things. Nice. So yeah, I guess if you have any questions, just like ask it on Piazza. Or... Actually, yeah, I don't know. Actually, yeah, just don't ask any questions. Okay. All right. Thanks.